I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you for the students. Just ask that you to bless this class and help us to understand a little bit more about modules over PIDs. In your prayer, Jesus, amen. All right, so get right to it in here. Actually, let me remove. And so one of the things I'm hoping to do this afternoon is to scan this so you can actually look at it. Although I was looking at section 12.1 in Dummett and Foote. Same, pretty much same. Slightly different notation, but much more or less the same. All right, so I'm getting to it. I have to remove these sticky notes that are leading me back to last lecture. Here we go. So I will remind you a few just general facts about what it means for R to be a PID. What's it mean for R to be a PID? What's PID stand for? Yeah, principal, ideal, domain. And what's that mean? Exactly. Every ideal is generated by one element. It's an integral domain. Is that right? Or wrong? Okay. What else can we say? I'm not sure about that, actually. I think I just added that. Is it? It is? Okay. Very good. Yeah. How about this? An element in a principal ideal domain is irreducible if and only if its ideal is, looking for maximal. So irreducible if and only if the ideal generated by the element is maximal. An element's prime if and only if it's irreducible. Remember, prime and irreducible become the same idea in a principal ideal domain. As you said, it's a unique factorization domain. It also satisfies the ascending chain condition ideals, and so does any finitely generated R module. Moreover, if M is n generated, then any submodule of M is also n generated. So these are the terms and conditions that we get to play with to start with. And then I'm going to describe a few of the basic things, state a few theorems, and then I'm going to jump and state the big theorem so we can try to start understanding it. Because, well, I will hopefully teach you bits and pieces of the proof of the big theorem. What I'm really actually more after is you understanding the central theorem of this topic. It's more important to understand the theorem than the proof, actually, in this particular context. Which is not to say I'm giving up on the proof just yet. That comes about a week from now. Let's hear. So, sorry, but you know how I am. Definition. Let R be a PID, M an R module. So 1, if n is submodule of M, then any generator of the annihilator of n is called an order of n. 2. An order of an element V in M is the order of the submodule generated by V. I think before we do anything else, you should tell me what the definition of an n is, right? What's the annihilator of n? So you tell me if I'm right or wrong. How about that? My thinking is it ought to be R in R such that Rn is equal to 0 for all n in n. Is this right? Okay. Are you trying to read into my tone? No, I'm not, because I value your input. Let's see here. So, let's see here. So any generator of the annihilator of n is called the order of n. I guess this must, let's see here. If we're talking about a Z module, right? Would that be allowed? Are the integers a PID? That's good, because that seems like an important case, right? So the order, for a Z module, the order would actually be an honest to goodness integer, right? So this terminology is not too foreign. But you should also realize here that if we were to, how about polynomials over a field? Maybe we should give some examples of PIDs, yeah? Is this a PID? It is, yeah. Can you think of any other interesting examples? I mean, obviously, F, right? Any field, I think, is a principal ideal domain. So, I mean, to call something in order when we're talking about a Z module, it's not too weird. But when we're talking about an FX module, I'm saying that the order could be a polynomial. To me, that's a little bit a strange use of terminology, right? Just a thought. Let's see here. Let's think about an example. What if we look at the Z module, Z3, Cartesian product with Z5. Suppose this is n. All right. What would be the annihilator of n here? Oh, that's not a good example. I wanted something like Z30 cross Z5. That's better. It's still not good. Sorry. Z30 cross Z20. There we go. That's what I wanted. Maybe it's still not what I want. Anyway, I'm going to try to stop changing it. So what would be the order? What would be the order of n as a Z module? 60. I guess it would be 60. Curses. Oh, and so order of n equals to 60. Right.
Well, it says any generator of the annihilator is called an order. So another order would be 20, another order would be negative.
Very good. Right. Yes, that's one of the abuses of language which we're about to engage in, which is to speak of the order.
Oh wait, no.
And yet.
Negative.
And yet there is not just one order.
Right.
Yeah, that's true.
Wouldn't be an order, but negative 60 would.
Negative 60. Yeah. But they won't be unique, generally speaking. Okay, so, but what's the order? I mean, what's the, as an abelian group, what's the order of n? 600. So this order of n being 60, it's not the order of the object as an abelian group, right? What is this order in terms of group theory? Do you guys remember? I might have ever talked about it, I don't know. I did talk about it some in terms of my told you guys a story about how I did encryption and it went badly because I picked an exponent which was one off the exponent of the group. So the group exponent is like the smallest power such that g to anything in the group goes to the identity. It will divide the order of the group, but it doesn't have to be the order of the group. Right? So this notion of order is more like group exponent for the abelian group, or subgroup in this case. All right, so there's that. Here's the theorem. Theorem 6.2. Let R be a PID, M an R module, 1. If alpha is an order of n, so maybe, maybe the more proper thing is to say this, other things, But anyway, if alpha is an order of n, which is a submodule of M, then the orders of n are precisely the associates of alpha. And we denote any order of n by On. And as is customary, refer to On as the order of n. So what he's saying is the custom is not to do this, which would be more logical, but instead to do this, with the understanding that that is not a unique choice. And I believe, Sam, you're right. Minus 60 is our only other choice as the only associate of 60 in the principal ideal of the integers is minus 60. As associates are related by units, and there's only 2 units to work with. Un and minus un. Sorry, I'm an idiot. All right, anyway, so where was I? We denote any order of n by On, and as is customary, refer to it as the order of n. 2. If M is the direct sum of A and B, internal direct sum here, then OM is the LCM of the order of A and the order of B. We certainly already know this in the context of Z modules, as that's abelian group theory. And when these are integers, this is a well-known theorem of group theory, right? That the, well, not exactly, but it's not surprising in some sense, this result. So he says we leave proof of part 1 for the reader. That seems like a good homework problem. For part 2, oh, didn't I say I wasn't going to prove things? All right. Would you like to see the proof of that? I don't know if it's, here we'll try. Part 2, we'll just do part 2. Suppose the order of M is equal to delta. Suppose that the order of A is equal to alpha. Suppose that the order of B is equal to beta. And suppose that lambda is the least common multiple of alpha and beta. I just do what I'm told. You want it to be gamma? I can put a gamma here, but then you're going to have to correct me when I write lambda instead of gamma in a second. There we go. Is that better? Okay, there we go. Put a gamma. Then, delta of A equals to 0. Oh, well, duh. Of course that's true, right? Why is that true? What's that? Yeah, delta is the annihilator of M, which means it annihilates everything in M. In particular, it annihilates A. It should also, what's delta of B? 0, right? See, when I read those yesterday, they meant nothing to me. But now that I'm talking to you guys, okay.
Because M is the direct sum, so delta B is the direct sum, and then alpha for A, beta for B, and then lambda for least common multiple.
Lambda for least common multiple.
I think that's what they were doing.
Maybe, but we've made it gamma because we have a desire to say alpha, beta, gamma, and I can respect that. So it's at least as, what's that, alpha, beta, delta?
Alpha, beta, gamma, delta.
Alpha, beta, gamma, delta. I'm going to stop listening to you today. Let's hear. Okay, imply that alpha divides delta and beta divides delta. Does that make sense? Okay. So gamma divides delta. But on the other hand, gamma annihilates both A and B, and therefore also M. Which implies that delta divides gamma. So you see we got this, we got that, hence gamma and delta are associates. In fact, I have this very fuzzy kind of deja vu feeling right now. I feel like I'm really, in some sense, remembering that this feels a lot like the proof we did for the corresponding, result in group theory, that the least common multiple of the orders of two elements is the order of a pair. I think it involved very much the same argument. But, of course, that was about integers and group exponents and such, but anyway, so there it is. The next theorem is a little bit technical, so I think I'm going to skip past that one. Well, let me do a calculation here. Okay, we're fine. So here's the next one, Theorem 6.3. Number one, if this is a cyclic R module, all right. What is that? What is a cyclic R module? So, in other words, the sentence is sort of tautological, right? Okay, so in other words, consider a cyclic R module with, but now this is substantial here, with annihilator. Alpha. Then the multiplication map tau that goes from R to the cyclic module generated by V, given by, what are we going to do, tau? And I'm going to use parentheses because I'm just not at the point in my life that I can omit parentheses on maps. I mean, I wish I was there. The book is there. So when you read the book, you'll be missing some parentheses, but that's cool. It just helps me to write the parentheses when I'm thinking about things here on the board. This is equal to R times V. So does that make sense? Annihilator alpha. Where would alpha be? What does that mean? What did this single bracket notation mean? What's that? Generated by alpha? In what sense? Okay, so this is inside R comment, right? So here, alpha is an element of R, right? So any two generators of this principal ideal are what? They're related by their associates, yeah. Okay. So what can you tell me about this map I just wrote down? So you would point out observation, the kernel of tau is what was it? So this guy. What else can you tell me about this map as it relates to the module, the cyclic module, bracket, bracket, V? Where we could go with bracket, bracket, V, bracket, bracket. But that seems unnecessary. Or Langle, Langle, V, Wrangle, Wrangle. I listed our four favorite terms. What were they? Monomorphism, epimorphism, the other one. Endomorphism, was it? No. Endomorphism, and then, of course, isomorphism. Of those four flavors, which would you like to say that tau is? A radical morphism? Is there some kind of joke there? It's very rad. I see I should not ask you questions today. Let's see here. I was looking for epimorphism as this is...
I wanted to say epimorphism.
You wanted to say it, but you sacrificed...
Epimorphism is like a less intense version of radical morphism.
Ah. So you're thinking it's epic, but what's more epic than epic is rad. Is that right? Okay, I understand now. So that was actually not that was an informed and more nerdy joke than I appreciated at the outset. So I can respect that. But yes, this is an epimorphism. It's a surjection because quite clearly, if it hits, it hits V, right? And of course, the image. I believe it's a. What would we say? Is it ring homomorphism? What is it? It's an R module homomorphism from the R module over itself R to the R module, the cyclic module generated by V. So it's an R module homomorphism, and I think we know that the image of an R module homomorphism is itself an R module. And the image clearly includes 1, and hence, clearly the image includes 1 times V, which includes V, which means that being that we're working in a principal ideal domain, it must contain that. Well, anyway, it is in fact a surjection, you're right. All right. And then, I'm sorry, I said I was going to go fast through this, and I'm not doing that. Hence, let me go on. Sigma bar going from R mod the ideal generated by alpha to this guy is what? Defined by sigma bar of R plus this guy equals this guy, RV, is an isomorphism. So by the usual set theory, mod by the kernel gets rid of the departure from injectivity. So in other words, cyclic R modules are isomorphic to quotient modules of the base ring. Now that's kind of interesting, right? So let's just put that in words again. A cyclic R module is isomorphic to a quotient module of the base ring. That's what one says. Quotient ring. Yeah. So we're taking R, mod and ideal. That's a quotient. What did I say? Oh, a quotient ring. Yes, I'm sorry. It's also a quotient module. Okay, yeah. All right. Well, anyway, any submodule of a cyclic R module is cyclic. And 3, if Langle V Wrangle is a cyclic submodule of M of order alpha, and again, as you guys have pointed out, that's redundant, but I think it's just for the sake of good pedagogy here, emphasizing, hey, that's a cyclic submodule of order alpha. Then for beta in the ring, we have that the order, I'm changing my order to a sigma, shame on me, order of Langle beta V Wrangle is equal to alpha over the GCD of beta and alpha. Also, we got that Langle beta V Wrangle is equal to Langle V Wrangle if and only if what's this notation? Parentheses, order V, comma, beta equal to 1 if and only if the order of beta V equal order of V, a period. What does that element parentheses mean? Yeah. Greatest common divisor. Exactly. This is GCD. Although it's a little bit disturbing that he didn't just write. So, like, what's up with that? Why write GCD over here, but then not write it over here? I don't know. Maybe it's just like I don't know. I'm not sure. Does this make, at least the equations make sense if it doesn't intuitively make sense yet? The order of that, let's see here. Could we think of an example that would make this sink in? Maybe in terms of integer stuff. Could you guys give me an integer kind of, basic abelian group theory Z-module example that would illustrate what's going on here? 35, huh? You don't know what to do with them. Why am I still listening to you today?
No, the greatest common divisor is 7.
Okay, fine. 14 and 35 has the greatest common divisor being 7, did you say? Yeah, I guess I believe that. All right. All right. Oh my goodness, why am I listening to you? Why did I do that? Let's look at, I don't know, maybe something like Z35. So let's see here. And we could look at, has that even got enough in it to do anything? What's that? We'll find out. Miserable. All right, so the order of, what do you want to pick for our V? How about 5? So what does that mean in this context? What's the order of 5? I believe it's, yeah, plus or minus 7. So we can say, so this has, all right, so I guess I need to pick a beta. To, what's that, 14? Okay. Then if we look at, isn't that 0? Okay, so that's 0, but maybe that's okay, right? Because allegedly the order of 0 is supposed to be, what was alpha here? The order of this thing is alpha, right? I believe alpha is 7. Yeah. I mean, thankfully, these words reduce to their usual meaning as they intersect with Z modules. Otherwise, coming up with examples would require me considerably more thought. Maybe it still does. It bears to be seen. But, okay, so we got alpha is 7 divided by what? The GCD of beta and alpha, which is 14 and 5. No? Oh, 14 and what? 7, which of course is 7 over 7, which is 1, which makes sense since the order of 0 is 1. So it works. And maybe this starts to make sense, that the order of this cyclic submodule is equal to this cyclic submodule is equal to that cyclic submodule if and only if the order of V and beta are relatively prime. Well, the order of V and the beta is relatively prime. So this is a set of things, right? So V and its associates are relatively prime to beta. That would mean you're generating the same cyclic submodule. And this would be true if and only if the order of beta V was equal to the order of V, which I believe means that V has, what can we say? Beta V is an associate of V, is that right? Yeah. Okay, I think this, after we sort through the language, starts to make sense. All right, moving along, at last, slowly but surely. Come on, stupid camera. Fine, we're not getting to the main theorem today. All right, I will plot ahead theorem by theorem rather than jumping the gun. You guys are happy.
Hey, at least we did some integer again.
Yes, we did examples. It's good. It's probably helpful in the bigger scheme of things. I must be patient. You know how I am. I just want to get to the interesting theorem. All right. One more interesting theorem for today. Which is on the decomposition of cyclic modules. So this is theorem 6.4. And here's how it goes. If U1, U2, Um have relatively prime orders. All right. Then the order of U1 plus U2 plus plus UM. Oh, this is an N, not an M. Sorry about that. N is equal to the product of the orders. Order U1. Remember, we defined the product of ideals in a principal ideal. Pairwise relatively prime. Yeah. Consequently, if M is A1 plus AN, where the submodules A sub I have relatively prime orders, then the sum is direct. Oh, that probably doesn't make any sense because I kind of buried an important equation that was in between what I wrote and what I wrote. In particular, this one. And the Langle U1 plus U2 UN wrangle is equal to the direct sum of Langle U1 Langle U2 wrangle Langle UN wrangle. So then the last statement in part 1 is less mysterious, yeah? In fact, the equation is written in the opposite order in the book. And also, this is part 1. Part 2, if you have the order of V is alpha 1, alpha n, where the alphas are pairwise relatively prime, then V has the form U1 plus plus UN, where the order of UI is equal to alpha I, and so Langle, the wrangle is equal to the Langle of U1 plus plus UN wrangle, which is of course equal to Langle U1 direct sum direct sum Langle UN wrangle. So this theorem shows how cyclic modules can be composed and decomposed by finding relatively prime factorizations of their order. All right. So perhaps we'll look at the proof of this. It might be instructive. I need to think about that some over the weekend. The next theorem past that is theorem 6.5, which says that if we have a free module over PID, then any submodule of that free module is free and has rank which is less than or equal to the rank of the module. That's a somewhat technical result that takes about a page and a half, maybe 2. Then theorem 6.6 says that if M is a free module of finite rank n, where R is a principal ideal domain, and if you have S with n elements, which is a spanning set for M, then it's a basis for M. Seems very natural. Theorem 6.7 says that if you have a free module of rank n, and if you have an n submodule, which is of rank k less than n, then there is a basis for M, which contains a subset for which multiples of the vectors in that subset by the ring, base ring, is a basis for n. So it's the basis theorem for subspaces is not quite the same, right? I mean, in vector spaces, right, you give me a basis. Is that, well, maybe it's still the same. Can we pick a basis for a subspace from a basis for this, from the whole space? No, we can't do that anyway. Right? That's even true for vector spaces. Like if you've got R2, you've got the standard basis, E1 and E2. Can you pick a subset of E1, E2 that gives you a basis for the subspace Y equals X? No, you need 1, 1, right? So you need a sum of those. So anyway. And then the next section is on torsion. And eventually, theorem 6.9, we get that for any finitely generated R module, it's the direct sum of a finitely generated free R module and a finitely generated torsion R module. And so that's the big picture, and then the rest of the section slices that more finely until eventually we get to the invariant factor or the primary decomposition theorem, which is what we're after. That will then lead us to either the fundamental theorem of finitely abelian groups, or also to the rational canonical form or Jordan form, those things, which is kind of neat. So anyway, we'll get there slowly but surely.